Somewhere in South Korea, behind 3 layers of security clearance, there is a room where light bends in ways it was never supposed to. No signs, no windows, no visitors. The engineers who work here spend their entire careers solving a single problem, one that most people don't even know exists. How do you hide a camera behind a screen that's already turned on? This is the story of invisible optics, and it starts with a rock, not just any rock. A cylinder of optical-grade glass, grown in a furnace at over 2,000 degrees, cooled for weeks in absolute darkness, and transported in a case that costs more than most cars. This boule, that's what they call it, carries 0 impurities. Not almost 0, 0. Because at the scale where this glass will operate, a single atom out of place will destroy everything that comes after it. The first thing they do is check it under polarized light, and here's why that matters. When you polarize light through perfect glass, nothing happens. The light passes clean. But if there is stress inside the material, even stress you could never see, never feel, never measure with your hands, the polarized light bends. It creates colors, ghosts of imperfection. The engineers are looking for silence. They want the light to say nothing. When the boule passes inspection, it meets a diamond wire thinner than a human hair. This wire doesn't cut the way you think, it doesn't saw, it erodes. Molecule by molecule, the diamond surface grinds through glass, while a mist of ultrapure water keeps the temperature stable to within a fraction of a degree. One vibration, one thermal spike, and the wafer cracks. What comes out the other side is a disc of glass so thin you could bend it between your fingers. 0.3 of a millimeter. You could stack 3 of them inside the thickness of a credit card. And yet this wafer needs to be flat to within a few nanometers, a distance so small that if this wafer were the size of a football field, the highest bump would be shorter than a blade of grass. That flatness doesn't come from cutting, it comes from polishing. Chemical-mechanical planarization, a rotating pad soaked in a slurry of colloidal silica particles, each one measured in billionths of a meter, slowly erasing every hill and valley from the glass surface until it becomes, for all practical purposes, mathematically perfect. But here's the thing most people miss. This glass is not the lens. This glass is not the sensor. This glass is the invisible layer. The piece that will sit between the camera and the world, hidden under a living, breathing OLED display. And if it's not perfect, every photo taken through it will carry a ghost, a haze, a blur that no software on Earth can fix. After polishing, the wafer enters a vacuum chamber. And inside that chamber, something almost magical happens. Atoms of metallic oxide are ripped from a target by a plasma of argon ions and deposited onto the glass surface, one atomic layer at a time. This is anti-reflective coating. You've seen it before, that faint purple shimmer on high-end camera lenses. But at this scale, the coating must do something far more demanding. It must make glass disappear. Not metaphorically, optically. The coating is engineered so that the light reflected from its top surface and the light reflected from its bottom surface arrive exactly out of phase. They cancel each other, destructive interference. The reflection doesn't dim, it ceases to exist. And now comes the part that separates a $5 billion facility from everything else on the planet. Micro-lens fabrication. The coated wafer is spin-coated with photoresist, a light-sensitive chemical that hardens when exposed to ultraviolet radiation. A photomask carrying the micro-lens pattern is aligned above the wafer with sub-micron precision, and a flash of deep UV light burns the pattern into the resist. After development, the exposed areas dissolve, leaving behind thousands of tiny circular openings. Reactive ion etching carves these circles into the glass itself, and then in a thermal reflow oven, surface tension reshapes those flat-bottomed craters into smooth convex domes. Each dome is a lens, a perfect microscopic lens, thousands of them, arranged in a hexagonal grid so precise that it could only exist because a machine placed every single one. These micro-lenses will gather light that passes through the gaps between OLED pixels and focus it onto the sensor below. Without them, the camera would be blind. With them, the camera can see through a screen, but a lens without a sensor is just a piece of shaped glass. In a parallel cleanroom, silicon wafers are being sliced, inspected, and singulated into individual CMOS image sensor dies. Each die is a miracle of semiconductor engineering. Millions of photosites arranged in a grid, each one capable of converting a single photon of light into an electrical signal. The dies are bonded to ceramic packages, connected by gold wires thinner than spider silk, and sealed beneath infrared cutoff filters that block the wavelengths your eyes cannot see, but your camera shouldn't capture. And here is where the two rivers meet. The sensor module receives its lens barrel. 5 precision glass elements, stacked and bonded in a sequence that took years to optimize. Voice coil motors provide autofocus. A gimbal mechanism provides optical image stabilization. Each module is tested, calibrated, sealed against dust, subjected to thermal cycling that simulates years of use in minutes, and tested again. The modules that survive, and not all of them do, are ready for integration. A CNC machine mills a pocket into the smartphone's aluminum mid-frame. The tolerances are measured in microns. The camera module drops in with almost no clearance. Its flex cable connects to the mainboard through a zero insertion force connector, so small that the locking lever is operated with a tool, not a finger. And then the display goes on. The OLED panel, impossibly thin, partially transparent in the camera zone, is laminated over the module. And just like that, the camera vanishes. You cannot see it. You cannot feel it under your fingertip. The display pixels continue right over the camera zone as if nothing is beneath them. But beneath them, everything is happening. Light from the outside world enters the phone. It passes through the cover glass. It passes through the OLED pixel layer, squeezing between sub-pixel cathodes that are less than 10 microns apart. It passes through the diffraction compensation layer that corrects for the interference patterns created by that pixel grid. It passes through the micro-lens array. It passes through 5 optical elements. It passes through the infrared filter. And finally, it lands on the sensor. 147 layers of engineering between the subject and the image. Now the calibration begins. The phone faces a color chart under standardized D65 illumination. Through display, color accuracy is measured and compensated. Flare patterns created by the OLED diffraction are mapped and fed to the neural processing engine. Low light sensitivity is tuned to account for the 30 to 40% light loss caused by shooting through a display. HDR algorithms are adjusted. White balance profiles are rewritten. Autofocus speed is benchmarked against targets at varying distances. The OIS gyroscope is paired to the stabilization actuators on a vibration table that simulates the cadence of human walking. Every single phone is calibrated individually, not by batch, not by model. Each device receives its own optical fingerprint, a unique correction profile that accounts for the microscopic variations in its specific camera zone, its specific display, its specific lens stack. This is why the process costs what it costs. This is why the factory exists. And here is the part they don't advertise. Most of the engineering in this camera is not about capturing light, it's about recovering from losing it. The display steals photons. The pixel grid creates artifacts. The compensation layers introduce their own subtle distortions. Every element in the optical path takes something away, and the AI reconstruction engine has to give it back, filling in detail, correcting color, removing noise, sharpening edges that were softened by passing through obstacles that were never supposed to be there. The invisible camera is not invisible because the hardware disappeared. It's invisible because an army of engineers made the compromises disappear. After final firmware is locked, every phone undergoes cosmetic inspection under magnification, thermal scanning to check for component hotspots, and a complete functional test that exercises every camera mode the device will ever use. Protective film is applied. The phone is placed in a molded tray, paired with its accessories, and sealed in packaging that is engineered with nearly as much precision as the device inside it. Boxes are grouped into cartons. Cartons are stacked on pallets. Pallets are stretch-wrapped for transit. And somewhere in a warehouse that stretches beyond what the eye can follow, a forklift carries the finished goods toward a loading dock, where trucks wait in silence. 3 months from now, someone will unbox this phone. They'll flip it over looking for the front camera. They won't find it. They'll open the camera app, switch to selfie mode, and see their own face. captured through a screen that shows no hole, no notch, no interruption. They'll take the photo, they'll never think about it again, they'll never know about the boule, the diamond wire, the plasma, the microlenses, the 147 layers, the 6-axis alignment, the neural reconstruction, the individual calibration profile written in a clean room they'll never see, in a country they may never visit, by engineers whose names they'll never learn. And that, in the end, is the point. The best technology is the kind you forget is there. Inside LG's secret optical lab, a process so advanced that the only proof it exists is that you can't see it.